When doing calibration, we typically compute weights based upon the standard deviation of the data that we have available, and then compute the user least squares with those weights to compute estimated values. I've got a very simple model here for which that approach actually would work perfectly, and you can see by looking at the data with the blue dots that basically it's all kind of not trending and it's pretty distributed pretty randomly, and we could get by very well by saying that the estimated standard deviation is the sample standard deviation, and the estimated value in this case actually is just the mean of the data. But what I want to do is I want to show you a new feature we've added with 3.1 and 8.1 in Stella that allows you to actually estimate the weights when you're doing maximum likelihood computation. So in order to do this, I'm going to set up a payoff. And the payoff is going to be a calibration payoff. And I'm not going to use the simplified approach. What I'm going to do is I'm going to set as a parameter the data, what I want to estimate. And I'm going to ask to estimate all elements of it as it's. And then for a comparison variable, I'm going to use estimated value. Again, all elements, so this match. And then for the comparison run, it's going to be the current run because we're actually going to do all of this in one place. It's going to be squared error and a comparison tolerance. Now, I also want to specify weights myself, so I'm going to uncheck that. Instead of having a weight of 1, I'm going to select the variable called very originally weight. Again, I'll use a star so everything has the same dimensions. And at that point, I just noticed that I have picked the wrong thing. Estimated value, I need a star here. At that point, you'll notice that there is now a checkbox that says compute full likelihood, optimize over weights. Since weight is here, that's exactly what we're going to do. And now if I go into the optimization choice, I'm going to use this payoff. And the optimization parameters I will choose are both estimated value, again for all elements, and it has a range of 1 to 5,000 built in, and the estimated standard deviation, again using a star, estimated standard deviation, again using a star, and it has its maximum values already built in as well. And now at this point I can run a optimization run and do an estimation over this, and what it will do is it will find the values for each of the different elements, and it will also find the values for each of the different weights that are used in the model, and we can see that we're getting pretty much the same values for the weights as we have expected. These weights are 2, 4 the population standard deviations are 2, 4, 6, 8, 10, and the estimated weights are roughly 2, 4, 6, 8, 10. Population values are 5, 80, 33, 67, 19, and we can see we're getting 4.8, 80. So roughly the same values for both of these. This is just a nice way to be able to estimate the standard deviation, or effectively the weight that you're using in doing the computation, at the same time as you're estimating the parameters that control the dynamics of the simulation.